So this is section 2 for honors pre-calculus, and what we're going to learn about is a constant percentage rate and exponential functions, exponential growth and decay models, using regression model to model population, and other logistic models. Why are we going to do this? Because exponential functions model many types of unrestricted growth. Logistic functions model restricted growth, including the spread of disease and the spread of rumors. So a constant percentage rate. Suppose that a population is changing at a constant percentage rate r, where r is the percent rate of change expressed in decimal form. Then the population follows a pattern. At p of 0 is our initial population, wherever the population is starting. And at p of 1, this is 1 year later. We're looking at what our initial population was plus the growth of the population at that point. Year 2, we have our population from year 1 times the population growth. And so the way this always works out is we always have our initial population times 1 plus our rate of growth, and that's a percentage rate, and t is always representing our time, sometimes in years, sometimes in decades. So if a population is changing at a constant percentage rate r each year, then the population growth is represented by this equation, where p of 0 is the initial population, r is expressed as a decimal, and t is the time in years. So tell whether the population model p of t equals 786,543 times 1.21 thousandths to the t power is an exponential growth function or exponential decay function, and find the constant percent rate of growth. Well, this is going to be, because the base would be represented as 1 plus 0.021, this is positive, and so this is r. And because r is greater than 0, this is going to be a growth function. So our population is increasing. Determine the exponential function with an initial value of 10 increasing at a rate of 5% per year. So looking back at our function, we have p of t equals our initial population times 1 plus the rate of change raised to the t power of the years. So the initial value is 10, so that's p sub 0, and it's increasing at a rate of 5% per year. Now you express that as a decimal to t. So this function would be expressed like that. And to simplify it, we'd have p of t equals 10 times 1.05 to the t power. And because it was increasing, that's why we had added that. If it had been decreasing, we would have subtracted 5/100ths from 1. Suppose a culture of 200 bacteria is put into a petri dish. So this is our p sub 0. And the culture doubles every hour. Predict when the number of bacteria will be 350,000. So if we're looking at p of t, and we have our initial population, and then this time when we're talking about it doubling every hour, that means basically it's increasing by 100%, or 1 every hour, and then t is going to represent our time in hours. So plugging in what we know, we have p of t equals our initial population times 2 to the t power. Now they want to know when the number of bacteria is going to be 350,000. So we're going to plug in 350,000 equals 200 times 2 to the t power. So when we divide by 200 on both sides, we get that 1750 equals 2 to the t power. Now you get to remember our logarithms. So we're looking at a base of 2, an exponent of t, and our power of 1750. So if you remember, you write this as log, base 2. The power is 1750, and you set that equal to the exponent, which is t, not 2. So in order to figure out what t equals, you do, in your calculator, you put in log 1750 divided by log of 2, and that's going to give us how much time that's going to take. So I'm going to go ahead and do log of 1750 divided by log of 2, and we get that it's going to take 10.77 hours. Before the number of bacteria is 350,000. Okay, use the population data in the table to predict the population for the year 2000. Complete with the actual population of approximately 281 million. So at this point, if you're watching the video on a computer screen, and you can pull up the notes on your iPad so that you can see the list that I'm about to put in the calculator, that would be a good thing to do, because we're going to use this data and put it in our calculator and actually do an exponential regression so that it will produce the equation for us. So let's first of all talk about what we're going to put into our calculator, because this is our initial population at 62,900,000, and so we're actually going to call this the year 0. And it's going up by tens, so when we put this in our calculator, we're going to say 1900 is 1. So really, t is going to be represented by decades in this case. So we're going to put in 2, 3, 4, 5, and we're going to keep these numbers just as they are, but we need to remember that this is being modeled in millions. So here are all of the ordered pairs that we're going to put into our calculator. So let's go to our handy dandy calculators now, and let's go to stat, and edit. And I'm going to clear everything out of that list and clear everything out of that list. So we're going to put in the ordered pairs 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 6, 7, 8, 9. Now we'll go back up to the top and put in the y values that go with those. So our list 2 is going to be 62.9, 76, 92, 105.7, 122.8, 131.7, Okay, now make sure when you're done entering your list that you have an even number of x and y values, or your calculator is going to yell at you. Now let's talk about what to put into our window. So our list 1 and list 2, list 1 we want to go from 0 to 9, but if we think about where the year 2000 is going to be, that's going to be where x is equal to 11, because that's 110 years later than 1890. So we're going to have our x values go from an x minimum of 0 to an x maximum of 11. And then for list 2, 0, we can put in negative 50 if we want, but we want it to go up to approximately 300. So let's go ahead and do that. Let's put in an x minimum of 0, an x maximum of 11. Let's put in a y minimum, oh, x scale. X scale can just be 1. Let's put in a y minimum of negative 50, a y maximum of 300, and let's have it going up by a scale of 50. And let's go ahead and look at the scatter plot. So let's make sure that that's turned on. So let's do second stat plot, and let's turn it on. Let's look at our graph. Oh, apparently I have some equations in there that I need to get rid of. Alright, so there is our stat plot. And we know that this is an exponential growth function, so this is the point at which you're going to go to stat, and you're going to go to calculate. And this is going to be an exponential regression. So let's go down until we see exponential regression. There we go. So it's 0. So we want to do an exponential regression using list 1 and list 2. And let's go ahead and store our equation so that we can see it on the graph. So we want to store it in our variables, our y variables. It's a function. We're going to store it in y sub 1. Now we're going to enter again, and now it'll calculate it for us. So we get that A would be 70, basically. B is going to be 1.15, so we have about a 15% growth rate for the year, because that's 1 plus 0.15. And now let's look at our graph and see how smooth the curve is that's fitting that. And that's pretty good. So let's quit out of here, and so that's how you would do one of these problems on the calculator. So exponential growth is unrestricted, but population growth often is not. For many populations, the growth begins exponentially, but eventually slows and approaches a limit to growth called a maximum sustainable population. So a high school has 1,500 students. 5 students start a rumor, which spreads logistically, so the S of t equals this logistic function. So like we talked about, we'd have a y asymptote at y equals 1,500 and 0, because it maxes out at 1,500. If we only have 1,500 students, it can't go beyond that. So it models the number of students who have heard the rumor by the end of t days, where t is 0 the day the rumor begins to spread. So how many students have heard the rumor by the end of day 0? So basically we're looking at S of 0. Well, this is going to be 1,500 divided by 1 plus 29 e to the 0 power. And e to the 0 power is just 1, so we end up with 1 plus 29, so that's 1,500 over 30. And so day 0, basically 50 students hear the rumor by the end of day 0. So how long does it take for 1,000 students to hear the rumor? So in this case, we're setting 1,000 equal to our logistic function. So to solve this, I'm going to multiply by this whole quantity down here. So I get 1,000 times 1 plus 29 times e to the negative 9/10 t equals 1,500. Now I'm going to divide by 1,000 on both sides, so I get 1 plus 29 times e to the negative 0.9 t equals 3/2. Subtract 1, and we get 29 times e to the negative 0.9t equals 1/2. And now divide by 29. So we get e to the negative 0.9t equals 1/58. So now's the fun part where we get to use logarithms. And so e is our base, 1/58 is our power, and negative 0.9t is our exponent. So we're basically going to say log, and it's understood that that's a base e, but I'll write it there in case you don't remember that. That's our base. 1/58 is our power, and that equals negative 0.9 times t. So let's go ahead and calculate in our calculators the natural log of 1/58. So we're going to hit natural log of 1 divided by 58 equals, that's negative 4.06. And we're going to divide that by 0.9, by negative 0.9. And we get 4.5. So what does that mean? That means about halfway through the 5th day, halfway through the 4.5 days into it, 1,000 students have heard the rumor. And that's it for this section.